Scott Virgil has been a Freeslate customer for a while. So in 2007, he started the Caltech Center of Catalysis Synthesis, and he supports all of the research labs there, the chemical labs there at Caltech. The work he does whenever I see him present is phenomenal, both the variety and the potent work, the valuable work that he's doing. So I'm very excited to see what he has to say for us today. So please welcome Scott. I've really enjoyed working with Freeslate from when I got started with the Catalysis Center at Caltech. I've told people stories that when Caltech decided to start a Catalysis Center, they first went to Freeslate and purchased the core module 2 systems, both in a dry box and a benchtop system, and had the systems delivered and everything ready to go, but they had no one to take care of them. So I happened to be available about 3 months later, and they gave me this opportunity, which has been extremely rewarding and exciting, and it's been great to work with faculty and students at Caltech, and great to work with the engineers and scientists at Freeslate as well. So for today, I'm going to tell you about, first of all, our approach to doing high throughput research at Caltech, and I'm going to come down here. And I'm going to tell you a little bit about our approach to doing high throughput research at Caltech, and give you some examples of the applications that we use that for. All right. So we started with the Freeslate systems in the sub-basement buildings that I had set up the Catalysis Center, and this was funded by the Gordon and Betty Moore Foundation, and we first purchased Symix instruments and the analytical instrumentation. These are 2 pictures of the Freeslate core module system in a dry box and the analytical equipment that are in the Schlinger building. We, of course, had to move everything up a small elevator and glue all the dry boxes back together. I'm sure a few of you have gone through that experience. And now we have a combination of analytical and robotic equipment that we use for the experiments at Caltech. We have the core module dry box system and benchtop system. I think that's not my sound doing that, but that's okay. We also recently purchased the Freeslate Protege solid dispense system that we've been using for support of reactions and screens that we've done at Caltech as well. We have a few other knickknacks that do specialized types of reaction equipment, and then we have had to build out our infrastructure so that we can do screening, and that involves collecting archive of ligands and then preparing protocols for using the instrumentation for our system. I have a slide here that describes our educational mission at Caltech, and in academics, the types of projects that you are presented with, I think, are quite a bit different than in a company or in a pharmaceutical company or industrial setting. We have students bring whatever they have, and they're ready to go right then. So they often are bringing projects to do that are the same as some other student had done before. Can I do this other, this other student did this and it's in their thesis, can I set this reaction up? And we've tried to build that into standard workflow of optimization of ligands, catalysts, solvents, and that sort of thing. One of the big things that we do that I think has been very popular is to use the robotic systems to save time for graduate students. That seems a little bit surprising. Graduate student time is supposed to be incredibly cheap, but they still have to go home at night, and if they want to run their experiments overnight where they're sampling kinetics and things like that, we've set up the robots to do that. And then I'm going to tell you a little bit about some challenges that we have for screening discovery that I think are the challenges we have to address going forward. I have a goal that I realized not as early on as I would have liked to, but when students bring their chemistry and their ready to go with their first experiment, I need to have a plan to give them to solve their research problems by a series of successes. So nobody likes to have the first experiment fail. And the system that I've set up for using the protocols and using the robots is one where, the student shows up, I'd like to run this experiment. You solve that problem first on an initial scale that they can get going immediately on. And then the student brings you or the researcher brings you what they want to improve in the reaction. Well, I'd like the robot to do this. I'd like to be able to bring in my designs from my Excel file or so forth. And so when they're asking for that higher level of sophistication, that's when you bring in those topics that you have available to them. And they're always, if they're advancing along the learning curve about high-throughput experimentation, that's useful. And the other thing that I'm going to talk about quite a bit today is that the students are going to be performing their experiments in a hands-on approach. Students will, and researchers and postdocs will often run the Freeslate equipment without me even there. I don't even know they ran these things. They sign up on the web and they're ready to go. I come in the next morning and they say, hey, works great, or they may say, hey, something went wrong. And then on the next slide, I'm going to show you that we came to decide that we need to use a single protocol for all of the experiments that the students might bring. Originally, student would come and say, I'm ready to go, I'm ready to start my reaction, this is what I'm ready to do. And I'd say, okay, wait, I got to write a whole new protocol. And then you start writing this protocol, but you can't be sure that there isn't some bug in that protocol. And I found that was an unsatisfactory way to proceed. You want to have a protocol that is going to handle most of the types of experiments that a researcher is going to bring to you. And they also want to have multiple options with data handling. In the beginning, they just want stuff as an Excel spreadsheet, but then as time goes on, they want to have be able to use more data and larger size data. I have a few of my training slides that I wanted to highlight because it makes it very easy. The Freeslate Automation Studio makes it very easy to present to students the features of the robot so they can learn that quickly. And I have my little pictures here with the stirrers to show how the rotary stirrers and the tumble stirrers work and everything like that. But the best feature about the Automation Studio is that, or that's shown in this slide, is that you can basically configure a screen for the computer that operates the robot that has everything that looks exactly like it is on the bench top, and that takes 30 seconds to explain to a student. This is the heater, this is the stirrer, this is the chillers, and they're ready to go. In addition to that, the protocols that we use can be accessed by selection off of this screen as well. So there's no ambiguity about, where is it on the computer, is that one still good, and so forth. So I really like that feature of Automation Studio. This is to describe how we approach a walked-up format and a library studio design on a single protocol. So when a researcher comes in and they say that they have something ready to go and they want to dispense these different solutions to these different positions or to a plate to make up their reaction mixture, and they've never seen the robot before. So we have our protocol, and I say, okay, I'm going to teach you how to do what's over here. This is an iterative protocol. It's task-based. They will enter, the thing says enter your first task. You have a text file. It's going to all print to a text file. When it's running the experiment, it's going to show you on the screen exactly what it's doing, and you explain to them what's going on here, and then they're going to go through these various steps. They have to select which arm to use, how many needles. They flush the needle and dispense. And the features of a program like this is any information that's entered by the user is in a variable that is sacred, it's stored, it's not written over or anything like that. And when they come back and they do the next round of the iteration, then that variable is shown to them in the status that they left it in. And they go through this dispense, and they are taught basically how to do the different types of dispense, whether you want to do an overshoot or air gap, whether you want to chase the sample in or so forth. And we can do, procedure, and this is a case where they can make up a system all like this. If they want to do additions to 8 different vials and they're all different volumes, then it's comma delimited. So we heavily use the run script command, or the Visual Basic script, where we parse out the information. So you type in 8B1 instead of typing in plate position 8, row 2, column 1. And with using run script, it makes the overall file size smaller and faster, and it's more useful for the researcher in doing that. So then this would be the last steps of the protocol. We're using the walk-up format, and you have other things that we brought in there where you have situations where if somebody has a plate that has 8 columns in it and they want to do 9 experiments, they can just bring another plate and say, well, you know, that plate that's 6 by 8 has 9 columns. And when the dispense takes off, it always looks for the next column in the next position. So these are examples where we can make the system more versatile in that matter. We have a number of experiments that we've run where instead of doing a library design or a library or a high-throughput screening, where you want to do slow addition, where we add 10 microliters 1,000 times to a reaction mixture. And so with this whole thing, we have one big loop in there that says number of repetition, delay time, and you can set up a kinetic aliquoting system in that feature just by saying, you know, run through that cycle 1,000 times. And that's been used a lot both with one reaction and with 4 reactions using the 4-tip needle. And I have a description of that as well. So we get through all that, and researcher is familiar with that, and they're always going to come back and say, well, I want to make my own design. I want to press go and go get a cup of coffee and come back and have everything run the way I want it to. So this is a case where we're going to teach them how to use a library design, Library Studio, which I think is a great program for researchers once they've gotten the initial idea of what's going on with the robotic system. And it's all in the same program. So over here we have a switch that if the user says this is L for library, type in your library design, away you go. Now with this executing a library design, many researchers that I talk to, everybody has their favorite tags. You know, we have a tag to do this, we have a tag to do that. So my case may be no different, but we use tags to both execute the types of specifications that we have in the walk-up protocol, like the different types of dispense and chases. Put a tag in for chase. It's going to look forward and find that chasing solvent, and then it incorporates it all together as one chase. And we also have tags for aliquoting, so we can set up a kinetics protocol if you have a reaction that you want to take aliquots of. It's going to know that those tags are in the overall library design, and then it's going to query you for where those things are and how you want to draw those out. So anyway, that's the protocol that I've used. Everybody has protocols that they use to work on different things, but I hope that going through these protocols gives you an idea about how we solve certain situations for our system. This is the last slide that I have of this showing the aliquoting of the system. So this particular one we used for setting up a crystallization screen. So we had, so in this case we had tags for doing layering of solvent and that sort of thing. We do the reaction at low temperature. We set them up in these types of, in the plates with the covers on. We let that crystallize, and this is an example of isolating a crystal of an intermediate in a palladium allylation. We've gone through and isolated crystals from these other palladium and ligand sources. And we've also used this for optimization, in this case taking aliquots of reactions for optimization of Kroll synthesis. So here's an example where we're mixing perfluorobenzaldehyde and Parole. These are cases for where you just get a complete mixture of oligomers, not always very controlled at all. We need to control that so that they're end capped on either end of it, and that the distribution favors the oligomer that we want. We went through the screens with Library Studio designs that involve change of pearl-to-aldehyde concentration, change of TFA, catalyst concentration, and temperature, and so forth. So this is our favorite one that we have published in the paper, where we get 25% yield of the intermediate oligomer, and then we use DDQ oxidation, where we have to find out what is the best conditions and additives for the DDQ oxidation. So overall, we only got 17% yield, but this is an improvement over what was out there, and we use that to make multiple grams of this pyrrole ligand. This is an example showing two examples of this slow inverse addition, where in one case we're adding a solution of the anion of this oxazole compound, and we add it to a whole bunch of different wells that have different additives in them. In another case, we have additives of different metal impurities, where we're trying to optimize the synthesis of a platinum hydryl chloride compound for platinum catalyzed olefin reactions. The little black vial in here is the sodium naphthalenide that's dark colored, and then all these are the platinum dichloride precursor. And we do, this was 1,000 additions, where we take the robot and we run through and do 10 microliters each. One of the projects that we've worked on most is our projects involving olefin metathesis. We have a Kinetics Run Protocol that we use regularly to evaluate different catalysts for which ones work better at the lowest catalyst loading in parts per million, and which substrates work best for which catalysts. So this is an example in the picture here. In the diagram, we have a waste plate, we have the reactions in triplicate. So there's four different substrates here, and each one's in triplicate. And then we have a waste plate in the pictures shown here in this small picture, but on the next page we have an actual movie going through here. So the system that we came up with, we took the four needle probe, and we set that, instead of being a 9mm separation, we set that to draw from 4 scintillation vials simultaneously that have each of the substrates for this reaction. And then over here are the reaction mixtures that are in with the catalyst already in there. And the catalysts are green and purple and so forth, but there's only 10 or 20 ppm or 20 to 100 ppm in here. So when we look at solutions, they're colorless. This adds the substrate to the four different ligands, and then after it's all done, the other arm, the left arm, is going to come over and do all of the aliquoting to the plates that have ethylvinyl ether in the quench, and it's going to fill up these two plates with time points. We take that to the GC and we go with that. So that's an application that we use for in a number of runs, and 2 or 3 different students have used this procedure. When they make a new metathesis catalyst, they want to find out what's the best catalyst for this reaction. And Kevin had worked out conditions for getting the reactions to give, reproducible plots. We had to try different ideas of, are the vials open, are they closed? We have problems with evaporation. That's obviously a problem that we always have in kinetics to solve. So we couldn't go higher than 40 degrees in temperature, but in this case we were able to get plots that show the different initiation and propagation features of the different catalysts, and we could compare which catalyst was most effective in that case. In a more challenging case, we do ethenolysis with methyl oleate to give these two decene and this decenoate compound. And we started out with doing methyl oleate, where we were able to get down to 1, 2, or 3 parts per million with turnover numbers in the hundreds of thousands. And then this is going to be carried on at Materia, that's in Pasadena, working on olefin metathesis. And what we sent them is that we can get from with 10 ppm, instead of having this type of situation, if we use these new catalysts, conversion to the same compounds. Obviously, a more difficult case to get to the low parts per million catalyst, but that's where we're at right now with that. We also have a screen where we just are screening which catalyst is best. So we have all the different colored catalysts, and we go through and make 6 plates on that. This is a screen that was done entirely with that walk-up protocol, because we can go up to 6 plates with that, set up the reaction mixtures, and let those run. Okay, so the case where we've had to use a different protocol other than the walk-up protocol is primarily in cases where we needed time-stamped kinetics, meaning that instead of just saying, wait 2 minutes and then go get the sample, when we have reactions that are running on a really short time scale, we need to have a protocol where every time something happens, then we're delivering an exact time, and those times can be used for the analysis of the data, and they can also be used to precisely say, at this time, add this other reagent. This is a polymerization reaction where we are using 2 different substituted Organometallic compounds. We come in with the catalyst, we polymerize one, we wait a certain amount of time before we add the second one. We're trying to optimize that to get the best polymer profile. And if we work up the reaction after a short period of time, we get one catalyst formed. In a longer period of time, we get a different catalyst polydispersity. So that was work that John Matson had worked on in that case. I'm going to skip through a couple of these applications, but we've done reactions with the Stoltz group on allylation. We have cases, the most interesting feature here is that we had to set up a situation to filter the samples through silica before we put them on our chiral columns, because the materials couldn't be directly added to the chiral columns. So we used a slurry system, and we transferred the samples through silica gel filters and used that for analysis. And by that way, we were able to screen various types of ligands for the optimum activity for these reactions. And in the more recent case, we found much better results with these lactam-type substrates that we could come up with what the best solvent screen or what the best substitutions were for that. So in the case of ligand screens and catalyst screens, we've had to come up with over 500 catalysts and ligands, and we have a pretty good method of bringing that into our workflow with our existing situations, but the acquisition of the Protégé instrument has allowed us to screen catalysis reactions where we have pre-prepared ligand solutions that we bring to the reaction, and then we're able to use bases like potassium carbonate or cesium carbonate or sodium phosphate where we screen different coupling reactions, and those we bring in from the solid dispense from the Protégé system. And these are cases where we're doing a kinetic resolution to get the optimum enantioselectivity on that. So that's pretty much what I wanted to present as far as our applications of the system. We're always looking at, I made a slide here that we're always looking at trying to get to the most efficient screening of reactions with the smallest volume. So here we have 20 mil vials that we started with, things like 1 mil vials, half mil vials, and so forth. But these types of plates that we were able to get from Freeslate, we're able to do reactions in the 100 to 25 to 100 microliter range, and that's allowed us to screen reactions more efficiently and not have to waste precious ligands when we do these screens. Okay, so I have talked about most of the examples here, and I wanted to thank you and open up the floor if you have any questions about this. I want to thank the Freeslate researchers and engineers. They've always been extremely helpful in providing us new opportunities and new ideas for how to use the instrumentation, and the new instruments they come up with have been vastly more effective in solving our problems.